A quick follow-up video on how to use the formula to evaluate the area of a triangle. So let's take an example to start with. We are given a triangle which is traced by the point 1, 1, 7, 7, and 5, 6. So to get a clear view of what we are actually doing, it's always better to plot the points as correctly and as accurately as we can manage. Right, so let's plot the first point as 1, 1, which would be right there. You see I've already drawn it before. That's at 1 from the x and 1 from the y. For 7, 1, it would be at 7 units from the y and 1 unit from the x-axis, and this is 7, 1. Similarly, let me just write this as 1, 1 here. We've already discussed this. Similarly, 5, 6 would be 5 units along the x and 6 units along the y. So this is at 5, 6. This is a triangle, and we wish to evaluate the area encapsulated by the sides. That means we need to evaluate this area, like so. Alright, so we have to use the formula that we derived previously, which was, well, the area of a triangle turns out to be -1/2 times, well, you go in an order as xa, ya, xb, yb, plus xb, ya, and so on, xc, yc, plus x sub c, y sub c, x sub a, y sub a, right? And what is a, b, c, and yeah, what are all those subscripts? Well, the subscripts refer to the points that we have. So if this is our point A, this is our point B, and this our point C, that means this is our point A, this point C, and this point B and this point C. Then xa and ya represent 1, 1, xb, yb represent 5, 6, xc and yc represent 7, 1. They are the coordinates of the respective points. Therefore, we need to write them in an order. And if you see the pattern here, you're going from A to C like so. And if I go, like as I go down along vertically along the determinant, I actually go along the side of a triangle in the order in which we number them. So A to B is my first determinant, B to C my second determinant, and C to A is my third determinant. As you can see, it's B to C, and C to A is my third determinant right there. Therefore, in order to really evaluate this area, all we need to do is the following. Right, so the area should be -1/2 times, well, first determinant would include the coordinates of point A, which is 1, 1, and remember the arrow goes from A to B. So in the last line, or in the second line rather, we will write the coordinates of the point that follows up from the previous point, which is determined by the arrow, and the arrow points towards B. Therefore, the coordinates would be of B, so 5, 6. Similarly, for the second, now we're done with A to B, we move from B to C, and we write them in the same order. So we write 5, 6 there in the first line, and on the second line we write, well, the coordinates of C, 7, 1. In the last determinant, we go from C to A, back to A. Therefore, we have the same form, 7, 1 on the numerator, or not the numerator, but the first line, and the last line or the second line would be, well, 1, 1. So you see that the order kind of forms like so. Like this is the symmetry, and you go back to 1, something like that. So that's one way to kind of remember how the formula like spans out. Anyway, the last step is to evaluate the determinants. Well, the second last step, and then we have to add them up. So the first determinant would be, well, 6 times 1 minus, well, 5 times 1. This is the first determinant. Second determinant would be, well, 5 times 1 minus 6 times 7, like so. And the third determinant would be 7 times 1 minus 1 times 1, like so. We can add this up to get -1/2 times, well, what is 6 minus 5? Simple, 1. What is 5 minus, well, what is 6 times 7? That's 42. So 5 minus 42 gives you 37 with a negative sign. This is 5 minus 42, right? And the last well, the last term is 7 minus 1, which is, well, 6. We can use this now. We can actually further simplify this. So we get 6 plus 1 as 7, and the second term is, well, minus 37. Now, what is 7 minus 37? Well, 7 minus 37 is, I'll write it here, is, well, negative 30. And if you see that the negatives now cancel out, and 30 divided by 2 gives you 15, so the area must be, well, positive 15. So that must be the area. We can actually check it at this point using the definitions of the area that we already know. So just erasing all this calculations for a while, we can actually work out how the area actually matches up with what we know about the triangle geometrically. And by geometrically, I mean, so if this is a triangle ABC, then the area of a triangle is half base times, well, height. So if you write this again, we must now substitute for the base and then the height corresponding to the base. Right, so I already see that there's one side which is very convenient to work with, which is the side AC. Now, AC is actually parallel to the x-axis. Therefore, if you want to measure the height of B with respect to AC, which we will denote by this term as the height there, well, that height must just be this blue distance. And that would be related to the y coordinate. So, therefore, the base now becomes this length, AC, and the height becomes, well, the y component of B minus this distance right there, which is 1 if you look at the coordinates of A and C. They are both at 1, they're at, well, something comma 1 and something comma 1. So that means this height is always 1. It's like the triangle is shifted by 1 unit from the x-axis. Let me just declutter all that. Anyway, so that's the base. Let me, in fact, write what the length of the base is. So if this point is at 7, 1, and this point at 1, 1, therefore this length must be 7 minus 1, or 6. Therefore the base should be 6, and the height would be this. Now, if this point is at 5, 6, and this line is at y equal to 1, the equation of the line is y equal to 1, therefore this height would be 6 minus 1. That would be 5. You can work out the geometry, it would be 5 in any case. We can actually solve this out. 6 by 2 is 3, and 3 times 5 is, well, a happy 15. Same as what we got using our formula in coordinate geometry. So this is a small check that you can do at times when you have a clear symmetry and a very workable example in which you know the base, you know the height, and you can just check it to be spot on every time. Now, there are key facts that I think everyone should know when they are employing this expression or this formula. The thing is, if you want to employ this formula, you need to always go in a clockwise direction, like so. So remember, A to B, B to C, and C to A always follows a clockwise direction. If you go the anti-clockwise direction, you guessed it, the answer would actually be negative 15. But since we're measuring the area, we can always take the modulus of that value to reason out the fact that even though the sign is different, the magnitude is what counts. If you go by this expression though, and you explicitly write A, B, and C in a clockwise direction, A, B, and C, something like that, if that works out, then the answer will always be positive. If it's not, then you just take the modulus of that value. Say if you get an answer like minus 70, then you take the modulus of that value to give you 70 or 70. So the area would always be a positive quantity for that particular triangle, right? So that's how you employ this formula, and also verify it using the usual definition of an area for a triangle, half times base times height. So I hope this video helped, and good luck.